The second pillar I want to talk about is the matching the environment to compliance. The environment that's very difficult for any robotic system or machine is the environment where humans are in. How many of you visited Samsung automation line for semiconductors? Nobody?
That's no one.
Okay. How many of you visited Hyundai manufacturing plant for cars? Nobody?
Usually they don't allow us to be.
Oh, this is very sad. But you do understand, when you go to these giant factories, you're not, first of all, you're never allowed in because it's dangerous, it's a company secret. And third, the machines cannot work. They have highly optimized vision to make sure everything is running in perfect synchronization orchestration. So they might have a mock-up once for the visit, but we will probably not get you in. Why? The most difficult environment for any machines, let alone robots, is an environment where humans come in. Otherwise, it cannot go full speed, and they cannot predict your move. And now, what are we talking about? You're talking about robots helping you with doctors to do surgery, robots helping with elderly to pick them up from bed, robots helping you with house chores, not just vacuuming, but also house chores. How are they gonna know this is the safe environment? Not the authorized personal only locked doors. If you want to bring automation in our environment, your machines, your robots need to be as compliant to your motions as well as your physical need. That's why the soft robotics community is focused a lot on new materials that are inherently safe, which means inherently soft and stretchy. And how can it be soft and stretchy? Why is it important? Because it matches the mechanical property of our skin. Anything that's skin level of Young's modulus will allow us to actually wear it and be compliant to our motions. So this is an example of how we can put actuation embedded with sensing directly onto the skin. What I don't like here too much, I mean, it's great work we did with a Stephanie Lacour's group who developed the sensing part with the liquid metal. But the part I don't like about here is that you're talking about haptics and touch. How many of you guys like wearing gloves? You only wear it because it's cool. Why? First of all, you cannot touch your touch screen, but other than that, would you be able to run your experiment with a non-nitro glove? Even with a nitro glove, I'm not so sure if you prefer it, as long as it's not safe, as long as it's safe. For haptic devices, I think we should leave our fingertips as natural and as free as possible. But it's not always easy because we still need to give a haptic sensation. But even before giving haptic sensation, we also need to think about how many sensors we need to put on the body. More the sensors, more the info you would have. But any measurement of sensing of a wearable is only as good as where it's in place and how it's placed. And if you have so many muscles, so many movements, compound movements, it's very difficult to understand what are the measurements you take. How many of you actually had a shoulder injury? Nobody. Shoulder. Knee injury. How many of you are awake? Many, huh? Shoulder is very complex joint where it's not just ball and socket joint. You have a parallel mechanism, a transmission as well. So it becomes very difficult to train your muscles and get repair done. So this is an example of how we want to actually have multiple sensing from a single device. So it's a chromosense where Rob had an idea of putting together colored columns where by changing its mechanical disposition, whether it's stretching, bending, or compression, we can actually measure the compound reaction of mechanical reaction into a single sensing. We analyze the changing light by different chrometry as well as intensity of light, and then we install it on the shoulder and then the pelvis of Josie. And what we see is the two sensors here, and then the three green balloons represent the actuators where our wearable is inflated to support different motions. So when Josie is lifting her arm, it's measuring the bending as well as compression. And that allows us to actually help her to actuate the back support. And when both sensors are used, now Sagar is picking up a box with a very bad position. I don't know if you have the ergonomy class. This is a very bad position for your back. But the hip sack inflates up to help with the supporting the back. Normally, you would either use a camera-based system, so you're always monitored with a camera to have a beep beep, and then you're activating the wearable, or you would need multiple sensing, or you would just have a single sensor IMU that only measures where up and down, but it's not going to be able to decipher between the motion, that compound motion. And by having this direct two sensors, we're able to measure different motions directly. Not all systems need to be made of silicone or PDMS, as long as you have enough of the degrees of freedom to execute the task. And I call that still part of soft robots. And that's an example of your chopstick use as what's supposed to spoon. On Southeast Asia and East Asia, we use a lot of chopsticks. But in Europe, not too many. Actually, almost none. They only do it for fashion. Why? Because you can get a lot done with a flat surface. Knives, spoons. Especially if you're picking up sundubu or potato mash, potatoes, something soft and liquidy. So flat surface is a very good tool. Probably much better than a pointed chopsticks. Same thing for native robotic manipulation. Not all the robots need to have fingers for making manipulation tasks. Either they can have tweezers if you want to do very precise tasks, but flat surface-based manipulation is hugely overlooked. So that's why we looked at it, and it's partially because I'm traumatized from my early work of human fingers. I really didn't want to work with fingers, but manipulation is still a very important part of robotic research. How do you achieve this? Well, where do you use it in industry? Here. So this is the world's largest chicken farm in USA, and this is a company in Italy who uses exactly the same machine. In this company, chicken goes in live, it comes out like this. Everything is automated. Live chicken goes in, so you see no blood, no nothing. Live chicken, this comes out. And guess what? Up to here, complete automation. What do you see here? That's not automation, that's human. Why? This task cannot be done automatically. No robot manipulator is able to achieve this. It's so much work. I don't understand why we can have everything automated to this point, and now this is human end. Why? The reason is chicken meat to be this nice and clean and pretty looking to buy, it needs to be folded out in a flat surface. And that no robot's able to do it until now. So we've introduced surface-based manipulation so that we don't damage the nice shiny skin of the chicken meat. The idea is to have conveyor belt, that's fine, it goes place 1 to 2, but it's not able to change the orientation or the form or how it's laying. And the idea is to just still use flat surface, cushion surface, to translation, flipping, and rotation. And that's probably the first time you're seeing it. So what we're doing here is so that was our earlier work. At the time, I did not work with this European company and European consortium. We use a module-based pneumatic actuators to move around soft balls and then harder blocks. But now we're using a larger blocks to show movement on random objects. Soft, hard, deformable. And what can we do? I don't know if you made sujebi. This is how you make sujebi. But currently, if you were to use robotic fingers, that's not possible. Flat surface wins in terms of a soft, compliant surfaces. And so we've been looking at Rigid object manipulation with solid, uniform square blocks, much easier than the others. Soft flour batter mixture, slender, hash brown, cookies, even fish for your sushi cravings. And that's been quite exciting because what we have shown is that actually having this surface will allow us to actually work better with compliant objects rather than using a pointy, more precise manipulation. And actually, it's not a surprise. If you want precise operation, you want small contact area. But if you want softer, compliant operation, you need larger contact surfaces. And that's why we've been very successful with this operation. And you can actually combine this with high degrees of freedom operation with a multiple altitude. So if you were to have multiples of these and combine in a grid format, we can move obviously flat surfaces, but also flexible objects. So individually, and we can actually, so these type of cloth and clothing, they actually either get caught in between the lines or you're not able to move in the multi directions. But this is where we're actually controlling these origami platform to move around. And completely ununiform, non-box objects are also the case. And this is exactly why current levels of manipulation is not able to achieve non-uniform objects. So when you order things online, Coupang, Amazon, what do they come in? Ginormous boxes. Why? Because the machines need to carry this out. But if you were to have this highly flexible platform, I think you can really reduce the number and the size of the boxes that are used to do the packaging. And I know a lot of you are material scientists. One of the solutions is not only just rely on the design, but also designing your actuators with the different materials. So you probably are very familiar with different types of smart materials that are changing its behavior based on mechanical strains, temperature, UV, light, different atmospheric gases, pressure. But where can we go with this further without changing so much of material? Making metamaterial whichever material you choose. The metamaterial, probably you're also aware, is that it doesn't matter what your base material is, but by changing how individual modules or cells are shaped, you can change the behavior of overall system. And I think that's one of really the keys of designing next generation robot. So the idea is, instead of relying solely on mechanical, permanent magnet-based rotary digital motors, we could actually take advantage of these materials, regardless of what. It can be smart or just dumb iron oxide or silicon oxide or duraluminium, 6000 series. But if you can actually mesh it out or make a very specifically clamp the structures by creating very smart dissections of the holes, maybe you were able to create artificial skeleton, the brain, the electronic skin, or robotic joints that have very specific movement based on the design without having everything to be individually actuated. So you can have a completely under-actuated system from taking advantage of the material design. And we're quite excited about that because on that paper we talk about the dictating principles of these metamaterial design aspects and the dictating model. And so if you want to look at different solutions for endowing movement to your experiment, have a look at that paper. The third is a little different. This is where I personally believe I need to go. I don't know if you agree. Hopefully by the end of this, you can agree this is an area that's undertapped so far. But what do you see here? Okay, I'll pick on people who's sleeping at the back, all the way at the back, all the way at the back with a beige cap. What do you see here? Beige cap. Yes. What is this? It's a finger. Doing what? Marble. It's a marble. The finger pressing on the marble. Is it a human finger? What is it? Is it a pillow? Marble pillow? Or is it marble that looks like a pillow? Anyone else? What is this? There's a finger, and it's pressing onto the surface, and it looks like it's dented there. What is it? Is it marble, or is it marble printed pillow cover?
I think it's some meat.
Huh?
Meat to be the circle.
Right.
Yeah.
We don't know. I don't know. I told AI to create this. So if we don't know, how would your robot vision know whether this is a marble or pillow? It won't. Why? Such data sets don't exist online right now. And from camera, we cannot tell if this is a marble or a pillowcase. There's no way. No way. How would we know? I ask a question, you get 100만 won if you can tell if this is a pillowcase or a marble. What would you do? Go and knock on it. If it makes noise, you know it's marble. If it makes no noise, you know it's a pillowcase. We have to touch it. Currently, there is no existing data set that would tell AI what that is. And why do we knock on it? Because we're using our knuckles to get the vibration back to the body. We are using our skin to touch the texture as well as the heat, the temperature of the surface. Then we know from our previous information, our intelligence, not artificial intelligence, real lived intelligence, we can deduct that's a rock. How can we teach our robot this? How can we teach our robot to learn this? We cannot do it with a camera yet. Yes, you can get the thermal imaging. Yes, you can get some other ways of suspiciously detecting what this might be. But unless you make a physical contact, so far there's no way of understanding this.